So in the previous class, we have discussed how exactly to relate the semiconductors conductivity as well as mobility, and what are the various factors which are going to determine the conductivity and the mobilities. So now in this class, let us go to the another parameters, drift and the resistance. So now here you can see in the picture, okay, so it is the semiconductor slab whose dimension is starting from x equal to 0 to x is equal to L, and we have connected a battery E across this, and as well as the hole motion as well as electron motion, which are opposite in direction, is shown. And in this according to the dimensions, W is the width, L is the length, and T is the thickness of the particular semiconductor bar. Now all these factors are going to affect what is known as drift and the resistance. Okay, so therefore this particular picture, it shows what drift of electrons and holes in the semiconductor bar. So now this relation is usually known to you, the resistance of the bar. Okay, so the resistance of the bar, it is defined as, so capital R is equal to rho L by actually area. Okay, so area is nothing but here W into T. So therefore now rho is nothing but it is the resistivity of the semiconductor material. Okay, and length, of course L is the length of the slab that is considered, and W is the width and T is the thickness. Okay. So now as rho is inverse of conductivity. Okay, so therefore you can write in another form also. So rho L by Wt is also equal to L by Wt into, instead of rho you can write it as 1 by sigma, which is nothing but the conductivity. I have called it as equation. Of course there is only one equation, as it is important I have named it as 1, that's all. Okay. So now what we are going to trying to understand from this particular relation is, okay, so the drifting of carriers, it requires one criteria. Okay, what is that? Holes move in a direction of the electric field, but whereas electrons move in the opposite direction, and this is shown in the picture. Okay, and the electrons and the hole components of the current in the direction of the electric field. Okay, so as the conventional current is positive in the direction of the hole flow and opposite to the direction of the electron flow. Okay, so hence the drift current is constant throughout the bar. See now here the drift current is nothing but it is a current constituted by drifting of both holes and the electrons. Okay, and this drift current remains constant throughout the bar. Only thing is their movement of the direction of movement will be in the opposite direction, but whereas, okay, so it is constant throughout the bar. So now in the semiconductor bar, okay, so here there are two more parameters that you can observe, x is equal to 0 and x is equal to L. Now these are the two extreme edges of this particular bar. Okay, so you can assume that at x is equal to 0 the carriers enter, and x is equal to L they leave. Okay, so therefore in the semiconductor bar, for every electron leaving the bar at x is equal to 0, leaving the bar at x is equal to 0, okay, so a corresponding electron will be entering at x is equal to L. Okay, so whenever an electron leaves at x is equal to 0, so a corresponding electron will enter at the opposite end of the particular bar. So therefore, okay, so these are the two opposite ends. Okay, you can imagine here an electron enters, okay, as it leaves at the other side it will enter. So therefore the electron concentration remains same in the semiconductor bar at N. So what is N? N is nothing but the concentration for us. Okay, so this is going to remain constant throughout the operation. Okay. So in case of holes also, so as a hole reaches the ohmic contact, so this is the ohmic contact, okay, where the semiconductor bar is attached with this particular metal contact, that is the ohmic contact. Okay, so in case of holes also, so whenever a hole reaches the ohmic contact at x is equal to L, so it recombines with the electron, okay, and that is supplied through the electronic circuit or external circuit. Okay, so as and when a hole is reaching at x is equal to L, recombination will takes place with an electron. So therefore as the hole, this particular hole disappears. Okay, so again a corresponding hole will appear at x is equal to 0. Okay, so a hole recombines at x is equal to L point. This is the extreme end of the semiconductor bar. So as it recombines and disappears, at the same time another hole will be created at x is equal to 0th point, and thus they maintain what is known as space charge neutrality. Okay, so therefore at any instant of time it may be number of electrons or number of holes. Okay, so if an electron leaves at a point at the one edge, a corresponding electron will be created or entering at the another edge. Similarly, if a hole recombines at one edge, another hole will be created at the another edge. So therefore, at any instant of time you can say that the resistivity or the resistance of the bar is defined as rho L by W into T, where rho is the resistivity and it can also be written as 1 by conductivity. Okay, so this will happen for this applied battery E. Okay, when this is in operation, so you see that the concentration N of the carriers, it always remains same. Okay, so this is a very brief few points about the drift and the resistance. Okay, so next we will what move on to another important topic, that is the Hall effect. Probably in even on physics or some other related subject you might have heard about this. Okay, so here we are discussing this Hall effect, so with respect to our carriers in the semiconductor. Okay, see, now here there are, you just first observe the picture. It is a semiconductor bar, okay, having the length L, and the other dimensions are width W and thickness T. This is as usual corresponding to the previous pictures. Now here there are other elements also, like Ex is x component of the applied electric field, Ey is nothing but y component of the applied electric field, and Bz is nothing but the magnetic field in the z direction, and Ix and Ix, they represent the direction of the current in the x direction. So now with this setup, what we are trying to define here is, okay, so assume that a magnetic field is applied perpendicular to the semiconductor bar as shown in the figure. Okay, so therefore here Z is nothing but the perpendicular direction, therefore Bz represents the magnetic field. So if a magnetic field is applied perpendicular to the direction of the whole drift, in case of what? In case of a p-type semiconductor bar as shown in the particular picture. Okay, so then we are going to define what is this Hall effect. Okay, so now you should remember that it is a p-type semiconductor bar and a magnetic field is applied just perpendicular to that particular bar or the path of the holes. The Bz is perpendicular to the path of the holes. Now as this is applied, Bz is applied, there is a chance that the path of the holes tends to be deflected, because those holes will come under the influence of Bz, so therefore their path is somewhat deviated or deflected. Okay, so therefore now we will write what is the total force. So what is the reason for deflection? There should be some force exerted by this Bz. Okay, what is that total force then? Okay, so therefore the total force, see here it is there. Okay, so the total force on a single hole. Okay, so due to this applied electric field and magnetic field, so this is given by a general formula, F is equal to Q into E is nothing but applied electric field plus V into V. So this is the total force exerted on the single hole. Okay. Now in that we are taking the y component. Okay, so let Fy be the force in the y direction. First we are defining all the parameters, later on we will go to this Hall. Okay, so let Fy be the force in the y direction, So then in the y direction it has been shown that Fy component will be equal to Q into Ey, because we are taking the y component of the electric field. So therefore Ey now minus Vx into Bz will come into picture. So why this minus Vx into Bz is, this is because to maintain a steady state flow of the holes along the length of the particular bar. Okay, and in order to maintain that steady state flow of the holes, the requirement here is whatever Ey is there, Ey is nothing but y direction component of the electric field. Okay, so Ey is equal to Vx into Bz. Okay, so therefore Ey minus Bz is equal to 0. So that's why here the y component, okay, so it is defined as q into Ey minus Vx Bz. So minus is nothing but it is simply related with the direction here. That's all. Okay, then so now uh, we when we consider the net force, okay, so the net force will become equal to 0. That is from the previous thing. Okay, so Ey is equal to Vx into Bz, so therefore Ey minus Vx into Bz is equal to 0. Okay, now this electric field is set up, which electric field? Ey electric field. Now this electric field is set up when the magnetic field shifts the whole distribution. Now these words are little bit tough. Okay, so the electric field in the Ey, okay, it is set up when the magnetic field, what is the magnetic field? Bz. Okay, so when the magnetic field shifts the whole distribution, where is the whole distribution? Inside the semiconductor bar. Okay, so when Bz shifts the whole distribution slightly in the y direction. Okay, so there is a appearance of Ey whenever the magnetic field slightly shifts the whole distribution in the y direction. Okay, now this will happen because of the presence of magnetic field. If there is Bz is equal to 0, if Bz is equal to 0, then holes will be just flowing inside the semiconductor bar without any deflection. But whenever a magnetic field is applied, there is a deflection in the holes, and what is that disturbance that we observe is, okay, so the entire hole distribution is slightly shifted in the y direction. Okay, that too when, okay, so when Ey is greater than Vx into Bz, okay, the holes does not experience the net lateral force. Okay, so as they drift along the particular bar, when Ey, whatever the y component of the electric field is there, when Ey is greater than Vx into Bz, okay, that is when applied electric field itself is more than Vx into Bz, then what happens? See, you need little bit of imagination here. See, again you go to the picture. Okay, so Bz is perpendicular. You can imagine that holes are in this particular direction from Ix to Ix, that is from C to D end. From C to D end, imagine that holes flow is there. Now Bz is applied, so because of this Bz, the holes get deflected. Okay, they are slightly shifted in the y direction. But if our y component of the electric field is more, if Ey is more than Vx into Bz, that is Vx into Bz, then these holes, okay, from between C and D points, they do not experience the lateral force and they drift along the particular bar, that is drift along the bar from C to D point. So the establishment of this electric field, now you just listen carefully now, the establishment of this electric field Ey is known as Hall effect. Okay, so what is that Ey? Whenever this Ey is applied in such a way that Ey is greater than Vx into Bz, then holes will not deflect and they drift along the bar. In case if Ey is just equal to Vx into Bz, then there is a deflection of the holes. Okay, so therefore application of this electric field Ey more than Vx into Bz is known as Hall effect. Okay, so therefore because of this, the resulting voltage VAB, what is this? A and B are the other two faces of the semiconductor bar, and the voltage between these two faces is known as VAB. Okay, and that particular voltage VAB, which is equal to Ey times W into Ey, okay, is called as the Hall voltage. Okay, so first of all, what is a Hall effect? Hall effect is nothing but establishment of an electric field Ey more than Vx into Bz. And because of that particular setting, whatever the voltage that we see between the points A and B, which is known as VAB, and the value of VAB is Ey, okay, Ey into W. Ey into W, because Ey should be applicable to entire width of the semiconductor bar. Okay, so that particular voltage VAB, which is equal to W into Ey, is called as the Hall voltage. Is called as a Hall voltage. So therefore, you just observe the equation 3. What was equation 3? Ey is equal to Vx into Bz. So therefore, now from equation 3, what we have written, y component of the electric field Ey is equal to Vx into Bz. Okay, but from the previous derivation of the conductivity and mobility topic, what we have, J is equal to current density, J is equal to Q P naught into Vx. Okay, so what we have, J equal to Q P naught into Vx. So this part we have discussed in the previous topic, conductivity and mobility. From that only it is taken. Okay, so J is equal to Q P naught into Vx. Therefore, what is Vx? I am trying to take out only Vx. So Vx is equal to J into Q P naught. Very simple now. So therefore, now I will substitute that Vx in the Ey equation. So Ey is equal to now Jx by Qp naught into Bz. So what I am trying to relate is this Vx term, velocity in the x direction, Vx term, it is replaced by current density term. That's all. Okay. So in order to replace Vx, we already have a relation from the current density. Okay, so that's why. Okay. Now in this equation, Vx is replaced by J by Q into P naught. So Jx by Qp naught into Bz as it is. Okay. So now we also have, okay, one more constant it can be defined. What is that? Whatever 1 by Q into P naught is there, 1 by Q into P naught, let us call this as RH. Okay, so what is this RH? This is known as, okay, the Hall coefficient. RH is known as the Hall coefficient. Okay, so let us replace that 1 by Qp naught by RH. So therefore, now our equation becomes Ey equal to RH into Jx into Bz. Okay, so therefore, now our total electric field component Ey equal to RH into Jx into Bz. Okay, so thus whatever this Hall field is there, Ey is there. Now this is proportional to, okay, so this is proportional to what? Product of, it is proportional to the product of current density and magnetic flux density. This is visible here. Whatever Ey is there, it is proportional to J as well as B. J is nothing but current density, B is nothing but magnetic flux density. Okay, so therefore Ey is proportional to J into B, or Ey is equal to RH into Jx into Bz, where RH is known as the Hall coefficient. Yes. Hello.
There is some disturbance, ma'am. There is some disturbance, ma'am.
My voice is not clearly audible. Huh? Hello.
With that, some other noise is also coming, ma'am.
Just a minute. Now it is clear. Huh? Hello. Now tell
Yes,
me now.
ma'am.
Is it clear now?
Yes, ma'am. Yes, ma'am.
Okay. So we are just replacing some of the terms in Ey. That's all. Okay. So from previous equation, I was here. So we have writing this Ey is equal to Vx into Bz as our Hall field. Okay. Now we will take the same equation, Ey equal to Vx into Bz. Okay. But we know that from the current density concept, J is equal to Q P naught Vx. As it is a P type semiconductor, it is P naught. If it is a N type semiconductor, it will be N naught. Okay, so therefore what is Vx component? J divided by Q into P naught. So now this Vx is substituted here. Okay, and 1 by Qp naught is called as a constant, that is RH. So when you substitute this RH here, then Ey becomes equal to, okay, RH into Jx into Bz. Okay, so therefore what we can observe here is whatever our Hall field is there, it is just proportional to Jx into Bz, or Ey is equal to Rh into Jx into Bz. That is, it is proportional to current density as well as magnetic flux density. Okay, so and this whatever constant is there, Rh, this is known as the Hall coefficient. Now I have called it as a equation 4. And from equation 4, okay, so from equation 4, so you can still make some more equations like this. Okay, so what is consider this relation, Rh equal to 1 by q into p naught. So therefore what is p naught? P naught is equal to 1 by q into Rh. Okay, so what is p naught? P naught is nothing but the whole concentration, that's all. And also from equation 4 you can write one more representation for p naught. So p naught is equal to what is this, Jx into Bz into q by Ey, using this equation. So using this equation, okay, so again you can replace p naught in terms of, okay, you can write p naught in terms of j, b, q as well as Ey component. Okay, just a replacement of terms here, that's all. So therefore p naught is nothing but Jx into Bz divided by q into Ey. Okay, that is, if you want to know the whole concentration, you can write like this. So you can still write some more. You can further go equating, bringing some other parameters like current density and all. Okay, and it is also known that Jx, current density Jx is equal to, okay, so I divided by area. Okay, so we know that current density is nothing but current flowing per unit area. Okay, therefore I, when I write Jx, it is equal to Ix. It is not I into x, it is Ix. X is a suffix, x component of the current. Okay, Ix divided by W into T. W is the width of the bar and T is the thickness of the semiconductor bar. This is one relation. And also other relation is, the Y component of the electric field, Ey, is equal to voltage divided by width. It is because why? VAB equal to Ey into W. This we have defined in the previous voltage equation. Okay, so that's why it is possible to write now Ey is equal to VAB by W. Now using these two, so further it is possible to rewrite P naught like this. Okay, so in the previous page we have defined P naught equal to Jx Bz by Q into Ey. Okay, so now whatever Jx is there, you just replace Jx by Ix by Wt, into Bz whole divided by Q into what is Ey? Ey is nothing but VAB by W. Okay, VAB by W. So further you can simplify whatever W term is there, it will get cancelled. So remaining terms are nothing but Ix into Bz in the numerator, Q into T into VAB in the denominator. So therefore, totally the whole concentration P naught is a function of I, B, Q, T as well as VAB. That is all. Okay. So whatever the quantities are there in equation, okay, so they all can be measured. Okay. So Hall effect gives accurate values for particular carrier concentration. Did you understand now? So as all the quantities can be measured here in equation 5, the Hall effect, it will give accurate values for the carrier concentration. Okay, so that is whenever you are applying Bz, okay, it is possible to measure what is VAB. Okay, what is T, and T, it is a dimension or the geometry of the semiconductor slab. It can be measured always. Further, as VAB is there, it is also possible to measure Ix. So all are measurable quantities. Therefore, it is possible to calculate what is this P naught, carrier concentration. Okay. So therefore, at the lastly, if resistance R is measured, okay, so if it is possible to measure the resistance R, then it is also possible to measure what is the resistivity rho. Okay, so because we know that rho is equal to RL, R by L into W into T. Okay, so therefore, if you know what is R, you can just substitute other parameters also. So it is just a modification of the terms, basic terms. Okay, so this equation can be further written as R divided by L into Wt. But what is R? R is nothing but VCD by IX. VCD means where is VCD? See in this picture, VCD is nothing but the voltage between the terminals C and D. That is between C and D phase of the semiconductor bar. Okay, VAB is nothing but it is a voltage across VAB, this phase and this phase. Okay, so therefore, so once you know this whole parameters, okay, so it is possible to simply calculate remaining things also. Okay, so this R is nothing but V by I. Resistance is equal to V by I. V is nothing but VCD. Why it is VCD? Why particular it is VCD? Because you can see here that the whole drift is between C and D. The whole drift is between C and D, and BZ is perpendicular to that drift. Okay, so that's why you can measure the resistance for the flow of holes between C and D. Okay, so therefore here to calculate R, you can write VCD by IX. This divided by L into W into T. Now all parameters are known. So therefore you can calculate what is the resistivity of that particular semiconductor bar. Okay. So now this is what is your module 1. Okay. So just to recall what all the topics we covered in the module 1. I'm just going back. We started with the basic introduction. Okay, so this was your module 1. We started with semiconductors. Just a minute. Hello, am I audible now? Hello, am I audible now?
Yes.
Yes, ma'am.
Okay, so
Yes, ma'am.
this was our basic introduction. This was the introduction. So what is the origin of the atomic theory, Dalton's atomic theory, and then how it was improved? Okay, so what is the Bohr's model? What are the uh, criteria? Okay, and what is this shell concept? Okay, what is the nucleus and remaining all four shells? What are the basic things and all? And then we started with what the concept of Bohr's model postulates. Okay, so actually this is what is the basic for our further discussion, and we again discussed range of band or available energies, and then going to the structure in detail. Okay, so this all depends on the Bohr's model, and later on we started with exactly the first topic of your syllabus, that is bonding forces in solids. So previous all was just an introduction for the subject. Now exactly your syllabus begins with this bonding forces in solids, and we discussed various types of bondings: ionic bonding, covalent bonding. So and as well as how is ionic bonding in case of NaCl. Okay, so what are the structures in case of covalent bonding, and what is this metallic bonding. Okay, and then we moved on to exactly energy bands, and there we discussed what linear combination of atomic orbitals, and this was explained with respect to a silicon atom. Okay, the concept of linear combination of atomic orbitals is explained with respect to silicon atom, and how this particular mixing up of the bands or merging up of the bands at the outer shells is going to create conduction band and valence band. That also we discussed. So how the splitting and the merging of the bands creates the upper band and the lower band. Okay, the upper band forms a conduction band having 4n states, and lower band forms a valence band with the 4n states. Okay, so and later on the separation between these bands is known as the EG, which is known as a forbidden band. Now this forms a main feature of all our semiconductor material, and this was the picture in order to explain that particular concept. And later on we started with the how the materials are classified as metal, semiconductors and the insulators based on the properties of the bands and all. So when it is called a metal, what's the band structure, what's the band structure of a semiconductor, and what's the band structure of the insulator and all. And this is a brief points about the semiconductors, metals and the insulators. I think in the notes also I provided all the information in detail. And with this particular picture it is possible to clearly classify them. And okay, so this diagram is a must whenever you are asked to write about this classification. You will have to show this particular band diagram, okay, in order to write explanation for distinction between insulator, semiconductor and the metal. Okay, and later on we started with the direct and indirect semiconductors, what is the meaning of them. Okay, so direct band gap semiconductor and indirect band gap semiconductor, and we took help of so many pictures to understand the difference between those two. uh, and later on, electrons and holes. Okay, we started with EHP, what, how electrons and holes are formed, what is the meaning of EHP and how EHP is formed. Okay, and what happens this valence band, conduction band when EHPs are formed. Okay, and particularly about this particular equation. And then we started with intrinsic material. Okay, so how to define an intrinsic material, and how, what is this another classification, that is extrinsic material. And in extrinsic material we get acceptor levels and the donor levels, what are the meanings of those two. And later on with the help of so many pictures we try to understand how a donor level is formed, how an acceptor level is formed, in order to understand in detail the concept of impure semiconductor, that is extrinsic type of semiconductors. Okay, so then later on actually I derived conductivity and mobility part. So I think I took a live derivation class, and I have also given the material for that. And after conductivity and mobility, what I have is drift and the resistance. Today I just discussed, and last topic is a Hall effect. This is complete derivation only. This you have to learn. Okay, so this is what is the end of your module 1. Okay, and for the first IA, so when it is on Tuesday, na? Tuesday, you will have to prepare for this particular module.